Good afternoon. It's my pleasure to welcome you all to the Don P. Giddens Inaugural Professorial Lecture. My name is Ed Schlesinger, and I'm the Benjamin Rome Dean of the Whiting School of Engineering. And it is truly a pleasure to be here to honor Professor Jaafar El-Awady, a professor in the Department of Mechanical Engineering, the founder and director of JHU's Computational and Experimental Materials Engineering Laboratory. He holds a secondary appointment in the Department of Materials Science and Engineering. He's a member of the Hopkins Extreme Materials Institute. He's associate director of the Center on Artificial Intelligence for Materials in Extreme Environments and the Center for Integrated Structures, Materials Modeling and Simulations. He's also the chair of JHU's Engineering for Professionals Mechanical Engineering Graduate Program and the chair of the WSE Faculty Senate. So I tell you all that in particular because as I welcome his family, now you understand why he's never at home, because he's busy doing all of these things here at Hopkins. And I do want to welcome Jaafar's family, his wife, his children, and his brother. Welcome. Jaafar's research focuses on the fundamental understanding of the deformation mechanisms in materials. His findings have led to the development of better materials for aerospace, naval, automotive, and energy applications. And his expertise is primarily in the field of mechanics of materials for extreme environments, with a particular focus on developing advanced multiscale simulation techniques to predict the mechanical properties underlying deformation mechanisms, damage evolution, and failure in materials. You'll hear today about how acoustic emissions could potentially be measured to reconstruct a 3D view of the time evolution of deformation and failure in metals. It is a fascinating topic of tremendous practical impact, and I certainly am excited to hear more about it. But before we do, I'd like to take a moment to recognize my predecessor, or one of my predecessors, Don Giddens, for whom this inaugural professorial lecture series is named. Don Giddens was the 5th Dean of Engineering at Johns Hopkins and a professor of mechanical engineering. And like Jaafar, his career has been defined by a commitment to both research and education. And now, before we hear from Jaafar, it's my pleasure to introduce Grettir Tryggvason, the head of the Department of Mechanical Engineering and the Charles A. Miller Jr. Distinguished Professor in Mechanical Engineering. Grettir.
So it is my pleasure to introduce Nash M. Gonim, a Distinguished Professor Emeritus at the University of California, who was Jaafar's PhD advisor. Unfortunately, Professor Gonim cannot be with us, but is going to introduce Jaafar by video, I believe. And with that, Jaafar, maybe you can turn him on.
Hello. Hello. I'm very pleased to introduce to you Jaafar El-Awady for this prestigious professorial lecture. It's inaugural. It's an important moment in his life, and I think it's a great tradition to do that at Johns Hopkins University. Thank you for making this an important moment in Jaafar's career. Well, Jaafar joined my research group about 20 years ago. He was a young, enthusiastic, and energetic graduate student then. And indeed, I was fortunate to have him join my group and do his research under my supervision. The time then was very interesting. We had a number of students who prospered and became very well recognized worldwide. And Jaafar joined this group, which made it a happy, collegial, and exciting environment for everybody. Well, Jaafar background was really strong in mathematics, computations, and physics, and general engineering. So that actually prepared him for the task ahead. It was a very difficult task, and the task was to do some research on understanding fatigue failure in materials. During that time, maybe for almost 30 years or so before we started to work on this area, many experimental observations were intriguing, and they had no answers. For example, the formation of persistent slip bands, organized structures, dislocation mechanisms, and the connection between fatigue and crack nucleation, all of these were shrouded in mysteries. Well, Jaafar's work contributed significantly to revealing the mysteries behind these phenomena and to our understanding today of fatigue failure. I think his strong contributions and the development of his PhD topic, which was titled Size Effects on the Plasticity and Fatigue Microstructure Evolution in Face-Center Cubic Crystals. But this is a long title, but it's a very precise title for his work. Anyway, his work led to great enhancement of our understanding of why persistent slip bands happen in fatigued crystals. How do they contribute to slip? How do they contribute to localization of plastic deformation, things that cannot be answered by traditional mechanics or physics, and how that relates to the nucleation of fatigue cracks. Of course, the whole idea is to prevent fatigue crack from nucleation, and this understanding now can help us in the society to develop more fatigue resilient materials. In fact, I had in my group many students who graduated with a PhD. Also, we had many postdocs that come and go, many scientists and collaborators that come and go. It was kind of a hub for a lot of activities for several decades at UCLA. And I would say that Jaafar's work has come to be at the top of the echelon of this group of former students and research scientists who contributed to the high reputation of our group at UCLA. I'm indeed very fortunate to have him as a former student, and now I really enjoy being a colleague, an esteemed colleague with him. And I know that with his intellect, sharp mind, with his social and interpersonal skills, I have no doubt that he will continue to be a leader in our field, and I expect great achievements to come. Jaafar, in closing, I wish you continued success with your scientific endeavors, and I wish you happiness with your family, with your friends, and with your colleagues.
So the introduction that Nasser gave about fatigue is something that we've been working on for a while. It's been a passion. I've had an opportunity to meet a lot of the leaders that have been focusing on fatigue and fracture in metals since the 60s. So there's one of the more famous folks in the world of fatigue, Hayal Maghrabi, had came to visit at UCLA when I was a PhD student. I think I was a second-year PhD student at that point. We had a lot of discussions. He was already retired, but he was basically one of the leaders in the field of fatigue. So it got me very passionate about fatigue. Fatigue is a very important topic for a lot of engineering applications. A lot of the work that I've done when I was at UCLA was predominantly modeling, and we've been doing a lot of modeling on fatigue, and we've continued doing some of that work. For what I'm going to try to present today, I tried to choose a topic that we've been working on more recently. That's still focused on fatigue, and it's more predominantly focused on an experimental point of view of trying to understand fatigue and failure in metals. So, quite jumpy today. So fatigue. So why is fatigue important? This is some data that I've collected recently from the National Transport Safety Board about incidents that happened for aircrafts over the last about 10 years or so, or 12 years ago. And each dot here represents basically an event. The size of it basically represents the amount of casualty. The color represents the amount of fatality that happened in it. And then I'm basically choosing 4 specific cases here that represent actual cases that were incidents that were quite famous throughout the news media when they happened. So you can see this was actually one of the major events that happened around 2012, where basically you can see that at the tail end, a piece of the tail basically broke off. And that was quite interesting because actually the failure mechanism happened in a screw that was actually attaching that piece to the tail of this aircraft. And what happened is a very bad incident where eventually 20 people died on the ground. This was basically an experimental aircraft that was a race aircraft that they were using and they were showing off, and unfortunately fell into the stands and created significant amount of loss in life. These are other incidents that happened on Southwest and American Airlines. I think these two were actually Southwest. This was an American airline. And a lot of them were quite famous as well in terms of incidents. Fortunately enough, these 2 incidents did not have any fatalities. This one, unfortunately, had a fatality associated with it. And really, these 3 examples are very common and very classical examples of fatigue and failure that is very common in aircrafts, where basically what happens inside the turbine engine is that due to fatigue and fracture, what happens is that pieces of the engine break up as it's flying, which leads to explosions in the engine, and then the engine basically disintegrates. Fortunately enough, engineers have designed aircraft such that they can actually withstand some of these behaviors, and the aircrafts can actually land safely. So this actually happened above Denver, I think, and eventually the aircraft landed safely, but as you can see, it was a big incident. This one, unfortunately, I think when the engine actually exploded, the blades themselves that are used for the turbine blades, they flew off and unfortunately ended up hitting a passenger on the aircraft and led to a fatality. So it's a very important topic. This is a significant amount of events. This is 350 events over 10 years or 12 years. That's significant in the world of aviation. Aviation, it's a dangerous process. It's maintaining the life of people that are on these aircraft is something that is of significant importance. So it's a very important topic that is very still a topic that is influencing a lot of the work in the world of aerospace and material science engineering. So that's not the only example. There's a lot of different examples, a lot of big incidents that happened over the last 10 years. Again, this is just another example of a train derailment. I'm not going to pronounce it, but you know how it is, where basically the train basically got off tracks, and it was associated basically with a fatigue failure in the rails themselves that led to this derailment. This is another incident where basically in the oil industry, some of these pipes, these are basically metals again. What happened, this one was buried below, one of these was actually at the bottom of this river, and what happened again due to the tidal waves that are passing back and forth, eventually that led to fatigue loading on the pipe, and eventually the pipe fractured, leading to significant amount of pollution. And these are just examples of what happened. These happen very commonly. If you go look at NTSB reports about incidents and look through their database about fatigue issues, there's tons of them that happen very, very commonly that affect our everyday life. So fatigue is a very important topic, and for those that don't necessarily know what that basically means or how does it really lead to deformation and failure in metals, this is a simple representation of what really happens in fatigue. The simplest example is this idea of a paperclip. It's the cheapest example that you could do a fatigue experiment in your lab, in your office, I mean. Get one of these paper clips and just basically start bending it. And what happens is typically the paper clips, without bending, before you bend them, the surface is quite pristine, they're quite flat. And what happens as you continuously bend it, the surface basically where you're doing that bending starts roughening. And that roughness continues to increase with increasing numbers of cycles until eventually a crack nucleates and propagates and leads to failure. This is actually an experiment that one of my students did as an example just to show this. He has a paper clip. He basically bent the inner portion here and eventually led to fracture. But before it led to fracture, he took it inside the SEM before fracture and before he did the bending experiment. And actually after he did the bending experiments, and you can see that transition from the smooth, pristine type of surface to a very rough surface. And you can actually see from zooming in all these types of cracks that are forming. These are the precursors that eventually lead to this larger crack that propagates that leads to failure. This happens in all types of metals. It's a very similar behavior. So this is just a quite nice example to show what that behavior is. So what leads to this? Why this basically happens? To understand that, you need to understand that metals basically are multiscale beasts. Multiscale in terms of the structure itself of a metal is multiscale, and the deformation mechanisms are multiscale and multi-time scales as well, length and time scales as well. So this is just a classical example of showing this type of idea of multi-length scale and time scale behavior of materials. So if you're basically interested in the deformation of any metallic component, if you look at any component under the microscope with some high resolution, you will end up seeing the individual grains. Metals are basically composed out of different grains. The grain boundaries are actually defects. If you go into each one of those grains, you would see dislocation structures. These are, again, defects that are present in the metals. And then if you go all the way down to the atomic scale as well, you can still see those types of defects. This is an example of a twin boundary that has formed in a metal. And you can basically understand that, and this is something that the entire community has been working on for the last few decades. You can do experiments on trying to understand the atomic scale information, the defect kinetics, the subgrain kinetics of defects, the crystal level information, as well as the structural level information. However, unfortunately, in the world of understanding, it's very difficult to be able to really design on the modeling track, taking into consideration all these behaviors that happen at the lower length scales. So if you really want to understand fatigue, you really need to be able to upscale all that information and be able to manipulate and understand the physics of the different length scales and time scales. So this is really where my group's research is. But just to take you back to this idea of fatigue and fracture initiation, this is actually an example that was published about 10 years ago of looking only at the surface of a sample. I think it was a pure iron, if I remember correctly. It might be not iron, might be copper actually. But what you're seeing here basically is the surface. They reconstructed the surface roughness as the number of cycles increase. So after 100 cycles, you start seeing these bands that are forming on the surface, these basically extrusions and extrusions on the surface. As the number of cycles increase, you can see basically that these extrusions become higher and the intrusions become higher. And then eventually, this is a TEM image right around one of these ledges that have formed, these extrusions that have formed, and you can see that these cracks start initiating and eventually they propagate. Now, the intriguing thing associated with this crack initiation and that extrusion is that if you look at the microstructure, the defect structure that is within this range, which is called a PSB, which is a persistent slip band that led to that extrusion, it would look actually something like this. So this is a TEM image. This is Hale Maghrabi, the professor that I mentioned that is, I would consider him as the father of fatigue, basically was able to show that what happens for these extrusions, or what leads to these extrusions, is formation of ladder structures, representative ladder structures, that are composed out of dislocations. These dislocations are the defects that lead to atomic slip in the materials. And then the black lines, the black regions represent very high dislocation density regions. The white regions represent low dislocation density regions. So the dislocations, these defects that are in the material, they start aligning this specific structure. That structure becomes where localized slip happens. So the material slip creates that extrusion, and eventually that extrusion will be associated with stress concentrations, as well as that these defects eventually lead to the formation of other types of defects, basically vacancies and interstitials. These vacancies contribute to the formation of cracks. Those are at least the theories that exist in literature. It hasn't been necessarily quantified in a way, because a lot of these experiments have been done on a large scale. You take a big sample, you test it, you stop, you go in, you look at the microstructure, you try to understand what's going on. So you don't have an actual view of how the deformation is evolving in these materials. And this has been basically the issue. So if you look at the life of any component in service, whatever application that is, typically what happens, and we're talking about metallic components here, if you have an undamaged material that is pristine, just came out of manufacturing, and then now it's exposed to this type of cyclic loading, what happens is that initially the damage will continuously accumulate into the material as the number of cycles of the loading cycles increases. Eventually there is a stage of saturation where nothing really changes much in the material. And then eventually suddenly you get these cracks that initiate. The cracks then form what are known as short cracks, short relative to the dimensions that are related to the material itself or the component itself. And eventually there's typically a lot of these short cracks that form. If I forward quickly over here, notice there's a lot of these cracks with different sizes. A lot of them are short. Not all of them contribute to failure. Eventually, some of them will dominate, and that what leads to large cracks, and then the large crack propagate until you get complete failure. Now, we understand in the mechanics world, in the materials world, quite well, and we can actually predict quite well this behavior, the large crack propagation and failure. So this is really can be classified using what is known as Paris regime or Paris law. And you can really quantify and predict when failure is going to happen if you have a large enough crack that you can measure and quantify. Everything that happens below that, we have very little understanding of how they all correlate together. How does the accumulation of damage lead to saturation? What happens during the saturation that eventually leads to crack initiation? How do the cracks eventually propagate when they're short, that eventually some of them become those large crack and propagate? And you would notice that typically in a lot of cases, again, depends on the loading regime that you're talking about, but in a lot of cases, the component itself is spending a significant amount of time doing this, not doing that part. Typically, when you're getting at a large crack, that's pretty much it. You replace the component, and you move on. So it's very difficult to really be able to build that entire picture. So this is where my group comes into play. Again, this is that time length scale plot that I just showed you previously. And just to tell you that basically the focus of my group is really looking at these defect structures, understanding their kinetics, and understanding how they basically relate to each other, the defects, kinetics together, as well as how do the thermomechanical properties of the material are affected by these types of kinetics in the material. If you look at the length scales of interest, what we're really interested in is really trying to develop physics-based models that allows us to go upscale from the atoms to the coarse grain level where we can look at numerous defects in the sample such that we can upscale information related to the physics that happen in these scales into the upper length scale of crystal plasticity that eventually can lead to full component prediction later on in the design cycle. Another topic of interest in my group is really trying to develop in situ experiments that we can use to characterize the mechanical properties at these length scales. And the reason that I'm interested actually in these types of in situ experiments is for two reasons. One of them is that you can actually extrapolate a lot of physical information about defects during the formation at these length scales if you're able to do these experiments in situ, and that's going to be really the focus of my talk. But in addition, they allow us to directly provide a validation to the physics-based model that we're predicting, such that eventually all of that hopefully will lead to better predictions of a structural level deformation and failure of different types of components. The track that I'm going to show you today is really on this side, and I chose the experimental side for a specific reason. My background really comes from modeling, and as I said with Nasser Ghanim, all my work was modeling. The reason that I actually decided to do experiments is that the experiments that I'm going to show you today, I've been told by everyone that does these types of experiments that they're impossible to do. And the point is that I wanted to bring this up to the students. Don't ever believe someone if they tell you it's impossible if you think that you can actually do it. And I'll touch bases on that when I get to the end. So it's something that really drove me into this, and it is actually through my mentors that ended up pushing me to say, oh, you should be able to do it on your own. So what is the problem? What are we trying to do? So what I'm trying to do is really try to quantify any distinct signatures that either control or precede the initiation or the evolution of plasticity, crack initiation, and short crack propagation. So this is basically that entire regime that we still have a lot of open questions of how they end up leading to the idea of crack propagation and failure. So the idea of how we can explore this came to me through this idea of trying to design in situ experiments inside what is known as a scanning electron microscope. This is a microscope. You use electrons such that you can actually visualize materials at the micron and submicron scale. And what we've ended up doing is we had to design this type of experiment, which is a high frequency loading experiment coupled with acoustic emissions, because I think we can extrapolate significant amount of information through these types of experiments. So what are these experiments? I'll skip the discussion about the acoustic emissions for now. I'll get to that in a few slides later. But pretty much what you should understand is you have a nano indenter setup. This is a small setup that you put inside the SEM. This is basically what you're seeing inside the SEM. And what it is that you have an actuator there, you have a tip. That tip basically looks like this. That tip goes down and you can actually compress on samples. So this is what you're seeing here. You can fabricate specimens inside a bulk sample. So this is like a millimeter thick substrate of any material you're interested in. You fabricate these type of pillars in them. They can have pillar geometries. They can have dog bone type of geometries, depending on what you're actually trying to answer or type of experiment that you're interested in. And then you can do these experiments in compression or cyclic loading or in tension and so on and so forth. There's a lot of information that I'm going to skip just because of the time and given that this is not an entirely technical talk, but more of a general audience type of talk. There's a lot of more information that you should look into the publication over there if you're interested in the details of how we do actually cyclic loading, how we actually set up a setup where we can actually do these experiments such that we can do fully reversible experiment inside an SEM. So the two things that I was told that is impossible to do is how do we actually mount a sample that we can do fully reversible tension compression that would mimic what people do in a bulk experiment. The other one is SEM costs us $70 per hour. So if I want to reach millions of cycles, which is what happens for these materials when they fail, I need to do this fast because I don't have enough money to be able to pay $70 an hour for a few weeks. So we need to do this fast. So the way that we do it is using high frequency loading, which is an intriguing approach that existed for a while, but apparently no one has implemented it into the small scale world, which was quite unique when we published this work a couple of years ago. So this is basically the setup. What I'm going to focus on for the first part is this idea of cyclic loading inside the SEM. So we fabricate these dog bone-like specimens, and what we're interested in is really what happens at that specific spot, which is the gauge section. So this is actually a real experiment that I'm showing you here. So this is the sample, and what you're going to see at the bottom here is a counter that basically indicates that we're increasing the numbers of cycles. Cycle basically means it's a fully reversible tension compression cycle. This is done live inside the SEM. The surface is not entirely clear because there's some small vibrations, but you can vaguely see formation of lines that are forming on the surface over there. What I'm showing you on the plot over here is something called the dynamic stiffness. This is a measure that you get from the nano indenter as you do these experiments. It relates to the stiffness of the material. It's not a direct measure of the stiffness of the material, but it relates to that stiffness. And what is intriguing as you do these experiments and as you reach about 3 million cycles, you start seeing this deformation forming on the surface. There's defects that form on the surface. It's an extrusion and an intrusion, and it starts to propagate. And it's not only one, there's multiple ones that start popping. You'll see continuously all these background lines that show up. You'll see some of these forming, nucleating, propagating along those specific lines. Why along those specific lines? That relates to the orientation of the sample that we chose. Slip typically happens along specific paths in metals. So this is basically a line such that we know where the direction of that slip is likely going. Now what you're seeing on the right here is an interesting plot as well. So initially when nothing was happening, this was a straight hardening behavior. The material was hardening. You can see the dynamic stiffness was continuously increasing. This is something that is known classically in fatigue, that the materials harden when you cyclically load them, but without significant apparent damage on the surface. And it's only when that first event that happened with an extrusion, that's really about here when the curve started becoming nonlinear. And eventually that leveling off, that's what is known as saturation again in the world of fatigue. The leveling off is when there's not significant amount of apparent change in the surface roughness of the sample, and there's no apparent significant amount of hardening that is continuously, that is building up in the material either. So first, it was quite unique in the sense that this experiment basically allowed us to see the nucleation and the evolution of these slip bands. And just to show you what the sample looks like after deformation. So this is a 3D view of that same sample. And this is basically the sample after 8 cycles versus after 8 million cycles. And you can clearly see that each one of those precursor slip events that happened on the surface, the sample was initially flat. There was no apparent slip bands that are forming on it. After 8 cycles, you start forming them, and then they stabilize for a while as the material continuously hardens, and then eventually all these slip traces form on the sample, and each one of them is actually associated with interior cracks that are propagating. So each one of those, so what we did is we cross-sectioned this sample. If you look through the cross-section, what you see is these cracks that are forming along each one of those bands that are forming. And these are these small, short cracks that initiate in the material. Not each one of them is going to propagate and lead to failure. Eventually, one of them is going to dominate and lead to failure, as I'll show you in the next slide. Now, the reason that a lot of this community with the small-scale world, did not necessarily try to go down that length scale is that a lot of people would argue that whatever behavior you're seeing at these length scales, which is still quite large, 10 microns to me is quite large, typically people argue that there are a significant amount of size effects and the deformation mechanisms are different. What we showed with these experiments is that actually is not true. The exact same type of formation of persistent slip bands form the type of crack propagation along the outer boundaries of these persistent slip bands form, very similar to what you see with these types of dislocation microstructures that are observed in bulk scale. These are the classical bulk scale experiments that people understand in the world of deformation of fatigue. So what we're showing with these types of experiments is that, yes, there are size effects. We are going down in the scales. The life of the component actually is prolonged. But nevertheless, the types of mechanisms that form, the types of structures that form, the types of defects that form are exactly similar and mimic what you see in a bulk experiment. And thus, this allows us an opportunity to be able to do these types of experiments to understand what deformation and failure happens. So this is, again, another intriguing analysis that we were able to do with this. Through image analysis of what we're seeing on the surface, we could take one of these bands, and as you see, there's 2 features that happen. One of them is that they pop up with a certain width, so we can basically quantify what that width is. And if you go through these analyses of the different experiments that we did, the embryonic width, which is basically the initial extrusion that happens on the surface, seems to range between 2 microns and 8 microns for the sample sizes that we've been looking at. In addition to that, we can actually quantify the speed as these bands form on the surface and propagate, extending to the ends of, to both corners of the sample. You can quantify those speeds as well, and we can quantify the speed of these propagation of these types of persistent slip bands. In bulk experiments, interestingly, they have never been able to calculate these types of experiments. One is because you don't really see these experiments, you don't see the evolution of them. But so this was quite unique in that kind of sense, giving us that type of ability to first be able to observe it. Now, we've been able to quantify, or at least physically explain, what we think is happening in it. We still cannot see what's happening internally, but we think that the reason why you get these different sizes of embryonic widths of these persistent slip band hitting the surface, it really depends on where they nucleate relative to the surface. And given that it is only 2 microns, or the minimum size that we've been able to observe is 2 microns, that basically indicates that they always nucleate internally. They don't nucleate on the surface. We don't never see something that is much smaller than 2 microns and propagating. So that basically indicates that they have nucleated internally, propagated to the surface, and then they continue to evolve until they span the entire cross-section of the sample. Skip the image on the right due to the time. But if you take this a step further, there was no fracture in that experiment. We stopped that experiment. We were particularly focused on the persistent slip bands. We took this a step further and we continue cyclically loading these samples. So this is another experiment, but at a higher strain amplitude. And you can actually observe in this case, as the number of cycle increases, eventually a crack nucleates, the crack propagates, eventually creating complete fracture in the sample. So again, the same type of setup, same type of experiment. Now, if you look at the dynamic stiffness measurement, which I showed you before, and we're skipping up here to point to after we know that the crack has, or very close to where the crack, that big crack initiated. And what you notice is that the dynamic stiffness had been continuously increasing, and then eventually a crack initiated. This is where we first observed that crack forming on the surface from an external observation. And eventually, as the crack continuously propagated, the stiffness started dropping, which is something that, again, it's a common thing that you would observe. But then we thought, okay, how do we actually extrapolate information related to how do these cracks actually propagate? So we stopped the experiment. This was done through what is known as a constant strain amplitude, and we decided to drive this experiment with a constant load amplitude, because when you do the load amplitude control, you can actually measure the amount of displacement and the changes in the displacement associated with the crack opening or with the crack closing. So if this dynamic displacement is flat, that basically means that at the same constant loads, the crack is not propagating at all. But if it increases, that basically means that the crack is actually opening. because that now it's much more compliant, so you can get more opening. And if it's decreasing, that means that the crack is closing. And intriguingly, if you look at this type of behavior of the dynamic displacement versus number of cycles after we stop the experiment here before full fracture, you start seeing different types of behavior of that crack. The crack is level, nothing is changing for a while, and then suddenly an increase. Nothing changing for a while, suddenly an increase. Nothing changes for a while, and then suddenly the displacement decreases, which indicates that there's actually crack closure that happens as you continuously cycle the sample. But in addition, it's clear that the way that the crack propagates is through an avalanche-like behavior. The cracks propagate, stop, propagate, stop, propagate, stop continuously. So this was quite intriguing for us to visualize this and be able to measure these types of quantities and statistics associated with it, which I'll skip for now. Because when we were doing this work, what I was actually interested in is identifying what is happening internally in terms of all these cracks that are nucleating, and how do we actually identify what leads to one of them dominating and eventually leading to fracture. This entire experiment, although it was quite exciting when we were doing it, I realized that at some point it's not really giving us that information. We're really going to the stage where I'm observing a crack on the surface that is the dominant crack, that's the large crack. I'm not able to actually observe the small cracks. As you see, there's a lot of small cracks that actually initiated before that dominated crack formed. So then the question popped up of how do we actually look at that behavior? And I'll mention something here that relates to it. So earthquakes. Earthquakes basically are the earthquake behavior is exactly similar to plasticity in metals. All what it is you have plates, earth plates, and what happens is that you get sliding of those plates relative to one another. Those slidings, there's different types of earthquakes. One of them could be related to this normal faulting where you get the two plates shifting up and down relative to one another. Or you get this type of idea of a strike slip where basically you're getting shearing of the two plates relative to one another. This is actually an example of an earthquake that happened in 2006 after this was a major earthquake that happened near Christchurch. And what happened was that you get this huge wall that formed due to basically the sliding of the two plates relative to one another. So that's the slip extrusions that we see in the metals. Again, metals, the way that they deformed is through slipping. And these types of deformation that you're seeing over there, which I showed you and I called basically fault slips, these are nothing but dislocation slip in the world of metals. The major difference is that metals, we have specific slip directions that are predefined depending on the orientation of the sample. This is a representation of this simulation that shows how these slip traces form when you cyclically load a material. So this is a reconstruction from a discrete dislocation dynamic simulation. In the world of earthquakes, they do these types of measures as well, and they can actually measure the type of slipping that happens. But in addition, what they're actually interested in is these waves that are emitted associated with the propagation of these events. In the world of dislocations, it's very similar. The motion of these dislocations as they move, that slipping that happens in the material, induces an acoustic wave in the material. And that acoustic wave you can actually measure the same way that they do that in earthquakes. They put sensors all over the place, they measure the displacements. That's exactly what you can measure with dislocation plasticity. So this is where the acoustics came into play. Because with acoustics, the neat thing with the acoustics is that the acquisition rate that you have, the response that you get from those sensors that you put on the surface are on the order of 30 megahertz. The loading stages that we have, when we simply look at the load displacement, the acquisition rate typically is on the order of a kilohertz. So it's a significant amount of information that you can extract out of these types of acoustic emission measurements. Now, there are a few issues associated with acoustic emissions. There's background noise that you have to deal with. But there are ways to overcome this behavior. So the only difference here is that we basically have an actual acoustic sensor that is attached to the samples that we're interested in, and we can actually measure any acoustics that emit during the plasticity and the deformation behavior. So this is an in situ experiment. We decided to go simply to in situ microcompression before we talk about fatigue, just because it's a new setup that we tried to implement. So we wanted to understand, can we really quantify acoustics associated with dislocation plasticity? So this is an in situ experiment that we have. Basically, this is the experiment. What you're going to see is slip traces that are going to start forming and popping. And every time that pops, basically, you'll see in the voltage signal, which is basically the acoustic signal, these types of bumps that are happening. And what we're showing here is basically the stress time. This is regular displacement load calculations. Again, regular displacement load calculations. But the neat thing with this type of experiment, let me show you a close-up to one of these experiments. So these are basically just representing different stress strain curves. If you look at one of these stress strain curves in a very small spot here where there was some type of drop in the stress as you were loading, so what you're seeing here is basically a very close up to this part right about there. And you can see that the acquisition rate of the load displacement is basically each one of those dots. Every circle represents a feedback that you're getting from your actuator. But with the acoustic emission, this is what we're seeing during that event. So this is a burst. This is a burst of dislocation plasticity. And during that burst, you can actually see that there's actually multiple bursts that are happening internally that you would have never measured associated with the load displacement only. But with these acoustics, you're actually able to get further significant amount of understanding of it. In addition to that, and this is something that you typically don't get from the load displacement. So this is the stress versus time. Again, from the load displacement curve, versus the voltage, which is basically the acoustics. The straight line here represents the elasticity part. What is interesting is you get microplasticity events that happen during the elastic loading, and you can actually measure those behaviors. So this basically starts giving us significant amount of understanding of events that are happening internally in the material. Because notice now, it's not just visualizing what's happening on the surface, but I'm actually able to hear what is happening internally. So this is basically a curve that shows you some statistics associated with the measured acoustic emission energies versus time. This is what you would get from the load displacement. You can calculate the burst velocity versus strain. And you can look at the normalized acoustic emission amplitude versus the acoustic emission energy. Now, the intriguing results, again, there's a lot of data here that I'm not going to go through into too much details, but one of the very intriguing things is when you look at this curve here, it's color-coded, in this case, it's color-coded according to the strain level. You would notice that the blues are on top here and the reds are down here. So the big events, those that are associated with large amplitudes or large energies, these are the big earthquakes that are happening in the material. They typically happen predominantly at small strains. When you go to large strains, the amount of earthquakes and the earthquakes that you have are much smaller. This relates, we think, is related to the types of defects that are forming internally that are blocking the earthquakes from having a significant amount of energy or a significant amount of amplitude. So it allows us now to actually visualize the events themselves with a higher fidelity than the load displacement calculations. I should say all of this is actually brand new work that Mustafa has been working on. So this is still unpublished, and we still are doing a lot of analysis on these data. Another intriguing thing with these types of calculations that you can do as well is that you can go into literature. Literature has tons of theories associated with acoustics related to dislocations, and none of them have been measured, none of them have been quantified. But this allows us, again, going down to the scale of microns, allows us to go down to the scale of individual defects, and allows us to go in and quantify those types of theories. Are they correct? Are they not? Do they represent the behavior, or they need significant amount of understanding? So this is an example of the energy versus the velocity of dislocations, which basically says that the energy is basically potentially related to the square root, the square of a velocity. From our data, you can see that that behavior generally happens. You still get the y versus proportional to x squared, but there's a significant amount of scatter in the data as well that these types of models do not represent. So the big question is, how do we actually take this type of representation where there's significant amount of scatter in the behavior into these deterministic types of laws, which we think potentially with machine learning that could potentially help us in trying to come up with better understanding of these types of behaviors. Taking this a step further and then learning a lot from, again, what happens in earthquakes, you typically have this idea of pre-shocks that lead to a main event, and then after that main event, you typically have aftershocks. This is really, again, very similar to what we see in metals. So I'm showing you here a single drop. So this blue dot and this red dot represents what we define as an avalanche, a single avalanche when the material deforms. So this is a stress drop. And what you're seeing in the background here that is gray and yellow and blue, that basically is the acoustic measures that we have. And you can quantify and see that the biggest event that happened is this blue one or this black one here, where before it, there were a bunch of smaller events that led to it. And then after that big event, there were a bunch of smaller events that happened after it. So we can start quantifying this in the sense that these are pre-shocks, these are aftershocks, and this is your main shock event. In the world of earthquakes, actually, there's a significant amount of analysis associated with the statistics associated with the energies of the pre-shocks with the main shock, or the energies of the aftershock with the main shock. So this is, again, an avenue that we're trying to push forward with, that we think is going to be quite intriguing to give us that better understanding of what potentially is a signature for this main event. Like, what are the signatures associated with these pre-shocks? What is unique about these pre-shocks that lead to this aftershock? And then how do these, or lead to this main shock? And then how these aftershocks that form eventually contribute to a next main event as we go forward. So this is, again, as I said, this is really brand new work that we're working on, that we're trying to push forward with, and we're hoping within the next few months, Mustafa, that we can finish up the analysis and get this done. So I'll finish up with some future perspectives and where I think we are as a field related to this world. So this is just a funny cartoon, me trying to be funny about fatigue in metals. So, you know, when you're sick and you go to a doctor and you say, hey, I'm sick, they tell you, hey, just take some vitamins and exercise and go home, right? That's all what they say. They really don't know what's happening, right, in the material, in you as a material, which is really what we as a community in the world of metals, we think we know what's happening, but it's impossible to really correlate events. So this is a big issue. So the big question is, and this is something that a lot of folks here and a lot of folks in materials worlds have been pushing forward with, is the utilization of machine learning and artificial intelligence in that process of understanding, predicting, and design. So this is an avenue that we're going forward with as well, with the significant amount of data that we're generating. The problem is, typically when you look at machine learning and AI, so this is another cartoon that is quite funny. It tells you basically that the AI machines, when they started the war against humanity, they started using primitive types of weapons. Why? Because if you look through history, most wars were won through primitive types of weaponry. So the problem is the data, right, is not necessarily the right data that we want to learn from. So you need to be able to really generate the data that is very relevant. So the future perspective that I have is really, you need to be able to develop these types of unique tools that enable you to quantify that type of deformation and failure at those proper length scales and proper time scales that basically matter. You need to be able to connect those types of experiments with unique forward modeling efforts. So this is the physics-based modeling, which I didn't talk at all about, but this is another branch of what we do in the group. And that basically gives you potentially significant amount of data that then you can actually use to really learn and be able to come up with actually an AI process that is actually meaningful on meaningful data. So this is basically my perspective of where we are and where we're hoping to go throughout the future. I did mention in the abstract of the talk that we were trying to do reconstruction based on the acoustics. This is a work that we're doing with Tamer Zeki in the mechanical engineering department, where we're trying to utilize machine learning on forward models that we were trying to predict the acoustics, knowing what the defect structure that led to them. Can we actually reinverse the process and say, if I have the acoustics, can I actually reconstruct the material? And there is very promising work on that front that we're pushing forward with, that we think hopefully will couple with these experiments that we can actually extract further understanding of the underlying deformation mechanisms. So this is my scientific talk. I need to finish up with acknowledgements. As a professor, typically we like to acknowledge ourselves, always in any type of event. So this is just a classical example of a professor responding to a student that just was awarded a fellowship and congratulating himself for being a great mentor, right? So the acknowledgement really that I want to say is really these are the folks that did all these types of work that led to me being able to stand up in front of you guys and present this work. So this is a group of fantastic PhD students, current and former, as well as postdocs, current and former, that really contributed significantly to all the types of work. So I'm really grateful for all of them. I know that some of them are here. There's a bunch of undergrads, some of them are here, some of them have graduated already that have contributed as well, but trying to put those on an image or on one slide would have been too much. So, but I really appreciate all the efforts, and there have been really fantastic group of people to work with throughout the years. I really need to acknowledge the mechanical engineering department. I know that I cut off some of the students there, but The faculty are more important, so, and the staff. I'm sorry, I'm just kidding. So, by the way, Gratar, this is about 4 years old. This is before COVID, so we need a newer picture. So, but anyways, a lot of colleagues here that have served as mentors and collaborators and friends throughout my journey here at Hopkins. It's going to be difficult to name names because I'm sure we're gonna run out of time, and I'm probably gonna forget a few names. And it's not only the mechanical engineering department. I have had a lot of collaborations with the physics and material science department and civil engineering that I really appreciate those interactions and the mentoring throughout the years as well from our senior colleagues. Finally, the real acknowledgement in terms of mentors. These are the mentors that I had from UCLA with Nasser Ghanim. I really learned from him how to be a professor, how to be a nice professor with your students, how to interact with your students, and how to really be able to interact with the community as well. Chris Stiles was, sorry, this is a typo. Chris Stiles is a close collaborator. This is Chris Woodward, my postdoc advisor at the Air Force Research Lab. In addition to that group, those smaller pictures are not smaller because they're smaller because they had smaller contribution, but actually I was very hard to find pictures that are publicly released for people from AFRL. So the only ones that were there were small pictures that if I blow them up, they're going to be very blurry. So that's the only reason that they're smaller there. Chris is actually retired, so he's now doing a lot of hiking. So this was a recent picture that he took, I think last summer. But they've contributed significantly to my career. Mike Uchik, I have to give him a shout out because really all this work, when I first was envisioning this type of experiments, I actually went to a number of folks that do these types of in situ experiments, and I told them, hey, we want to do this type of experiment. Can we collaborate on that? And everyone came back saying, oh, this is very hard. This is very hard. I don't want to get into this. This is not going to give us anything that is useful. I talked with Mike, presented him my ideas. He's one of the leaders in these types of in situ types of experiments at the small scale. And his comment was, don't listen to them, go do it. And that's really what drove us to do this type of work and take the initiative. And I was very grateful that a bunch of funding agencies were willing to bet on this work and push forward with it. Satish Rao has been a long friend as well, that has been a collaborative, long-term collaborator with this group and when I was at AFRL and as well as when I came here at Hopkins. So he's been a great person that I've learned a lot of atomistic simulations from. He's really the brains on atomistics, and I've really learned atomistic simulations from him, which was a great effort. So very fantastic people, really contributed significantly to my career as an educator. I have to thank my family. I didn't put their pictures up because I know that this is broadcasted, so I didn't want to put their pictures up, but you can go to my Facebook page. I closed that even, but anyway, I want to thank them. They've been contributing significantly and allowing me to be able to do this, and coaching their teams as well has been a lot of fun on basketball and soccer that allowed me to get away from just being focused on science and research and academia. So I thank them a lot. And most importantly, I really want to thank my father, who passed away about 10 years ago. He was really the biggest mentor that I had throughout my years before he passed away. This picture was, to date, I think it was about 20 years ago. This is right before I started my PhD. Took this picture actually in Turkey. It's my favorite picture because it's the only one that both of us are quite laughing in it. And you can see that I'm much thinner back then. I was probably about 40 pounds smaller than I'm now right now. But really, I actually spent my entire childhood in his office at a university. And I dealt with all his students as an advisor when I was a kid back then. So I learned a lot from him. So I'm dedicating this to him. And with that, I'll stop here and thank you very much.
That's amazing work, really is amazing work. Any questions from the audience? Yes, one question over there.
You talk about earthquakes. There's a lot of energy in those waves going up. How about in your system? So look at the energy in the plasticity versus the waves.
There's a lot of energy, but relative to the sample size, it's relative to how many events are actually happening, but relative to earthquakes, there's completely different. They're not related by any means. Oh, we haven't done this on fracture yet. So the next stage of this work is to push this towards fatigue and fracture. The goal is to try to quantify what happens actually during crack initiation and the transition from plasticity to crack initiation to short crack propagation. We think that there should be specific signatures associated with it because we know that at least for dislocation plasticity, there are signatures that are completely different than twinning. The people have been quantified fracture on its own without looking at plasticity, but on a much larger scale. Those energies, again, would be larger because, again, you have a much larger surface area that is being fractured and so on and so forth. So it is still, there's still a lot of stuff to do there.
Thank you. Oh, one more question.
Very interesting talk. I'm curious about the last part of your talk. I wondered for earthquake, you can use multiple
Yes.
sensors to locate the epicenter. I guess for the small sample, probably much harder to do. Why not just do bigger?
So there are two answers. One is it's not very hard to do. The problem is the sensors that we have were not designed for these types of experiments. They were designed for bulk scale experiments with acoustics where you can put multiple sensors on it. So the sensor itself is as big as the entire substrate which is much larger than the specimens that we're interested in. So acoustics is not the right way if you want to get multiple sensors. If you want to do that, you should use laser measurements of the displacements on the surface. And it's something that we're thinking about trying to do as well in the future, where you can actually shine in micron-sized spots on the surface and getting the changes in the reflection of the wave from the surface, you can measure the displacements locally, which would give you much more accurate, by the way, less noisy data than what we're getting with acoustics. So we think that the future is really driving us towards trying to do something on that type of experiments rather than doing acoustics. Why not do it on bulk scale? People have been doing bulk scale experiments with acoustics. But the problem is you're talking about a significant large sample. You don't know where fracture is or cracks initiating. You don't see them because you're optically looking at it. You're not looking at cracks that are on the scale of microns that are forming. What we think with the in situ setup, we can actually see when the crack initiates. We can see when a slip trace forms on the surface, and we can correlate that with the changes in the wave signals as well. So we can definitively go back and say, this was associated with that. We know that the events happen on the surface multiple positions along the surface. Again, how does that location relate to the measurements associated with the acoustics? There's a lot of information that you can extract out of these in situ experiments that are very difficult to do from a bulk scale experiment. We'll talk. Thank you.
And sort of a, if you will, a souvenir of the event, I want to present you with this.
Thank you very much. Thank you. Thank you. Appreciate it.
Really, congratulations again. Congratulations, Jaafar, and thank you all for joining us. And please enjoy the reception right back there.
Thank you.